Hello everyone, welcome. My name is Sergio Zamora and I am a PhD student at Penn State University. Today I will talk about the lower semicontinuity phenomenon at the level of fundamental groups when one looks at Gromv-Hausdorff convergence. I will talk about how it fails in the non-compact case and show how some symmetry conditions can make it work again. This video consists of 5 parts. I will start talking about the relationship between Gromv-Hausdorff convergence and topology and give you some examples to show how they don't get along with each other. Then I will talk about the lower semicontinuity phenomenon at the level of fundamental groups, which happens to be the only bridge between Gromv-Hausdorff convergence and topology that works for general length spaces. As we will see later, this lower semicontinuity fails in the non-compact case, and trying to establish it will lead us to talk about convergence with symmetry, in particular convergence with discrete symmetry. At the end, we are able to extend the lower semicontinuity of the fundamental groups to the non-compact case whenever we have nice enough discrete symmetry. Part 1, Gromv-Hausdorff convergence and topology. Recall that a proper metric space is a space that satisfies the Heine-Borel theorem, that is, every closed and bounded set is compact. Gromv-Hausdorff convergence is designed to work with these kind of spaces. I will start with a very simple and general question. If we have a sequence xn of proper metric spaces converging to a space X in the Gromv-Hausdorff sense, what can we say about the topology of X, the limit space, with respect to the topologies of the elements of the sequence? As many of you know, the short answer is almost nothing. Why do I say this? Well, to begin with, every compact metric space is the limit of a sequence of finite metric spaces, just like in this picture. So every element of the sequence has a discrete topology, but the limit is an arbitrary compact metric space. This is way too degenerate for us, so from now on, we will only consider length spaces. But even for length spaces, this situation is not much better. As we can see from these two density theorems by Cassorla and Su, closed surfaces with Riemannian metrics are everywhere. The first theorem here says that sigma 1, the class of closed Riemannian surfaces that can be isometrically embedded in R3, is Gromv-Hausdorff dense in the class of compact length spaces. It says that for any compact length space you take, no matter how ugly it is, there is a surface in R3 which we can actually visualize that looks like your length space. Second theorem here says that the class of closed Riemannian surfaces of constant curvature -1 is also dense in the class of compact length spaces. This means that any length space can be approximated by a quotient of the hyperbolic plane by a discrete group of isometries. I want to remark that in terms of topology, closed surfaces are rather simple objects. Their homology and cohomology groups vanish starting at dimension 3, and all their homotopy groups vanish except for the fundamental group. Regardless of that, a limit of surfaces could be an arbitrary length space, a class so wide there is no hope in classifying. All this was for dimension 2. How about larger dimensions? Well, things get even crazier. Ferry and Okun approximation theorem says that if you start with an arbitrary closed smooth manifold Y of dimension at least 3, and X a compact length space with an ANR topology, if you don't know what ANR means, don't worry, it's just a very wide class of topological spaces, including all topological manifolds, finite dimensional Alexandrov spaces, and locally finite CW complexes. Then, there is a sequence of Riemannian metrics in Y converging in the Gromov-Hausdorff sense to X, if and only if there is a continuous map from Y to X, inducing a surjective map at the level of fundamental groups. This is impressive for several reasons. First of all, the dichotomy of whether we can or cannot approximate X by Riemannian metrics on Y doesn't depend on the metric structure of X, but only on its topology. In the particular case when X is simply connected, then Y has a lot of freedom. For example, if X is a simply connected compact Alexandrov space, and Y is any closed smooth manifold of dimension at least 3, this theorem implies that we can deform Y so that it looks very similar to X. Last thing I want to mention about this theorem is that it relates the fundamental groups of X and Y. A necessary condition for Gromov-Hausdorff convergence in this setting is that the fundamental group of Y has to be in some sense larger than the fundamental group of X, since it surjects. From the first isomorphism theorem, we get that the fundamental group of X is a quotient of the fundamental group of Y. Part 2, lower semicontinuity of the fundamental group. This phenomenon happens in general. We have this theorem, which is quite easy to prove, and says that if we have Gromov-Hausdorff convergence and some technical assumptions, Then we have surjective morphisms from the fundamental groups of the elements of the sequence to the fundamental group of the limit. About the origin of this theorem, in the year 2000, Christina Sormani and Wei proved some stronger results in this direction. Frank Cassorla, Steve Ferry, and Boris Okun, from the theorems I mentioned earlier, proved some versions of this theorem back in 1992 and 1995. And Bilderich Tuschmann attributes this idea to Celestin Rakotoniaina in 1985. However, I'm unsure about who first stated this result in its current form. An intuitive way to understand this theorem is the following picture, which you have probably seen if you have talked about Gromv-Hausdorff convergence before. We have a sequence of spheres with handles, or tori, converging to around the sphere as the handle becomes smaller and smaller. In this example, the fundamental group of any element of the sequence is SD2, but the fundamental group of the limit is trivial. This happens because the non-trivial loop collapses and disappears. What the theorem states is that the opposite cannot happen. That is, if we can find a non-trivial loop in the limit space, then this non-trivial loop has to be already present at some point in the sequence. Again, the fundamental group of the limit is smaller than the fundamental group of the elements of the sequence in the sense that for large enough n, the fundamental group of the limit is a quotient of the fundamental group of the nth element of the sequence. Now, I want to look a little more carefully at these technical conditions. We require that the limit is both compact and semi-locally simply connected. Let's see what happens if we remove one of these conditions. If the limit is not semi-locally simply connected, the lower semi-continuity of the fundamental group may be violated, as we can see from this example. We have the standard sequence of wedges of circles converging to the Hawaiian ring. When we take cones and double this sequence by wedging, we obtain a sequence of simply connected spaces such that the limit is not simply connected. So in this case, the fundamental group of the limit space is strictly larger than the fundamental group of every element of the sequence. Observe that the limit is not semi-locally simply connected at the obvious Oakley point. We can also see that when we remove the compactness hypothesis, the lower semi-continuity of the fundamental group does not hold. We have a sequence of ellipsoids that converges to the cylinder S1 cross R. Every element of the sequence is simply connected. However, the limit has non-trivial fundamental group. I really like this example because we get to see exactly what goes wrong in the non-compact case. Imagine you have a rubber band around an ellipsoid. We know how to contract it to a point. We just slide it upwards until we reach the top. On the other hand, if we try to do this in an infinite cylinder, we will just slide the rubber band forever without achieving anything. This is a natural issue when we consider pointed Gromv-Hausdorff topology, since for a sequence to converge in the pointed Gromv-Hausdorff sense, we only require the spaces to behave well in a certain neighborhood around the base point. We can observe that the middle piece of the ellipsoid looks very different from the top piece, and the pointed Gromv-Hausdorff convergence never gets to see that top piece. This wouldn't happen if we had groups of isometries acting transitively on the elements of the sequence. With enough symmetry, we may be able to reconstruct an entire space just by looking at a small piece, or that's the idea. This led me to think about Part 3, Convergence with Symmetry. With the example of the ellipsoids in mind, I thought that enough symmetry would force the lower semi-continuity of the fundamental group to hold, even in the non-compact case. Of course, I kept the semi-local simple connectedness hypothesis and conjectured the following. If we have a sequence xn of proper length spaces converging in the pointed Gromv-Hausdorff sense to a proper length space x, which is semi-locally simply connected, and each xn is homogeneous in the sense that there are groups gamma n acting transitively by isometries on the spaces xn, then the lower semi-continuity of the fundamental group would hold in the same sense as before. However, I quickly ran into this counterexample. We take y to be S1 with its standard length metric, and Dn to be the three-dimensional round sphere of radius n. We define xn to be the quotient of y times Dn by the diagonal S1 action. The spaces xn are all homeomorphic to S3, but they converge to the product S1 cross R2. So we have a sequence of simply connected homogeneous spaces whose limit is a space with non-trivial fundamental group. Therefore, a lot of symmetry is not enough to get the lower semi-continuity of the fundamental group. If you want to understand better these spaces xn, they are rescaled Berger spheres. You start with a Hopf fibration. The fibers have their regular length, but the directions perpendicular to those fibers become longer and longer until the Hopf vibration degenerates into the trivial vibration with fiber S1 and base R2. Anyway, I didn't lose hope and thought about this similar problem. Let Yn be a sequence of Riemannian manifolds of fixed dimension with Ricci curvature bounded from below and converging to a point. This is what some people call manifolds with almost non-negative Ricci curvature. If we take Xn, the sequence of their universal covers, it consists, of course, of simply connected spaces, and for every n, the fundamental group pi1 of Yn acts on Xn by isometries. In this case, I kept thinking that the limit should be simply connected. And there is a key difference between this conjecture and my previous failed attempt. In here, the action of the fundamental group of Yn on Xn is discrete. Part 4, Convergence with Discrete Symmetry. We start this fourth part with some definitions regarding group actions in metric spaces. For a non-negative delta, we say that a group action in a metric space is delta transitive if for every two elements x and y in my metric space, there is a group element G that sends x to a point in the closed ball of center y and radius delta. In other words, an action is delta transitive if every orbit intersects every closed ball of radius delta. Another important definition is the following. We say that a group action by isometries in a metric space is discrete if the orbits are discrete and the stabilizers are finite. I repeat, the orbits are discrete, and for every point, there are only finitely many elements of the group that leave that point invariant. In proper metric spaces, one can restate discreteness of a group action as follows. When we equip the group with a compact open topology, then it becomes a discrete topological space. The example I always keep in mind is the following. I start with a Riemannian manifold Y of diameter delta, and Y twiddle its universal cover. Then the fundamental group of Y acts delta transitively and discretely on Y twiddle. One last definition before we move on to the results. Assume we have a sequence Xn of proper metric spaces. We say that this sequence consists of almost homogeneous spaces if we have a sequence of isometric group actions such that the action of the nth group on the nth metric space is delta n transitive and discrete, with delta n going to 0 as n goes to infinity. That is, we have a sequence of discrete actions which none of them is actually transitive, but as n goes to infinity, they are closer and closer to being transitive. In such a case, we say that the sequence of groups acts almost transitively on the sequence of metric spaces. I want to point out that in general, a sequence of homogeneous length spaces is not a sequence of almost homogeneous spaces, since the group actions are not discrete in general. So this concept of almost homogeneous spaces is not a generalization of homogeneous spaces. An example of this setup is the following. If we start with a sequence of Riemannian manifolds converging to a point, then the sequence of fundamental groups will act almost transitively on the sequence of universal covers. So the universal covers form a sequence of almost homogeneous spaces. Now, in order to understand and eventually prove the lower semicontinuity of the fundamental groups in this setting, one first has to understand the limits of sequences of almost homogeneous spaces, which is the following general question. If we have a sequence Xn of almost homogeneous length spaces converging to the proper length space X, what can we say about the limit space? Another example of this kind of convergence is the following sequence of infinite graphs with shorter and shorter edges that converges to the cylinder S1 cross R equipped with the taxicab metric. Observe that the sequence of isomorphism groups of these graphs acts almost transitively on the sequence of graphs itself. Let me mention some more examples of this convergence with discrete symmetry, and we will notice some pattern. We start with G, a nilpotent Lie group that admits lattices, and equip it with an invariant length metric, could be Riemannian, Finsler, sub-Riemannian, or sub-Finsler. Then, the trivial sequence GGGGG converges to G, and we can find the sequence of lattices in G acting almost transitively on the sequence GGGGG. In the particular case, when G is S1 cross R, this example looks pretty much like the figures I just showed you. Another example comes from geometric group theory, and it is by Pierre Panseau and Misha Gromov. If we start with gamma, a finitely generated group of polynomial growth, and y its Cayley graph with respect to any set of generators, then the trivial sequence of groups, gamma, 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 acts almost transitively on the sequence of rescaled Cayley graphs y over n. In this case, the limit of the sequence is a simply connected nilpotent Lie group equipped with an invariant sub-Finsler metric, which is the asymptotic cone of the Cayley graph y. Coming back to the example with Ricci curvature bounded below, if we have a sequence yn of manifolds with Ricci curvature bounded below and converging to a point, then, as we said before, the sequence of fundamental groups acts almost transitively on the sequence of universal covers, and up to subsequence, the universal covers converge to a nilpotent Lie group equipped with an invariant Riemannian metric. This was proved independently by Vitaly Kapovich, Burkhard Wilking, and Emmanuel Brullat, Ben Green, and Terence Tao. As you can see, the pattern is that for sequences of almost homogeneous length spaces, the limit is a nilpotent Lie group. Let's talk about some results in this direction. First, Alan Turing showed that if the limit space is a compact Lie group, then it is a finite-dimensional torus. Turing's proof consists of essentially 4 steps. First, by Peter-Weyl theorem, X has a finite-dimensional faithful linear representation ρ. Then, for large enough n, the Gromv-Hausdorff approximations are good enough that we can recover from ρ faithful representations of gamma n over hn with hn very small normal subgroups. Observe that the representations ρn are all of the same dimension. Then, by Jordan's theorem, the groups gamma n are uniformly virtually nilpotent in the sense that they all have subgroups of fixed index that are nilpotent. Taking the limit as n goes to infinity, we get that the limit is nilpotent as well. The fourth step is just noticing that all nilpotent compact connected Lie groups are abelian, hence tori. For those of you who don't know about Jordan's theorem, here it is. It is quite elementary, but it is so important for our argument that it is worth presenting a sketch of the proof. The theorem states that if we have gamma a discrete linear group generated by its elements which are close to the identity, that is, the elements of gamma, within the ball of radius 1 over 10 around the identity with respect to the operator norm, then gamma is nilpotent. For the proof, a quick computation is required, which essentially shows that if we have two matrices A and B close to the identity, then their commutator is even closer to the identity. In other words, if A minus the identity is small, and B minus the identity is small, then the commutator minus the identity is quadratically small. How does this give us nilpotency? Well, take A to be the element of gamma closest to the identity. Observe that, to do this, we require gamma to be discrete. Then, by this formula, A commutes with everyone in the group, because otherwise a commutator will be even closer to the identity, contradicting our choice of A. Define G0 to be the trivial subgroup, and G1 to be the cyclic subgroup generated by A. Then take G2 to be the subgroup of gamma generated by G1 and the element of gamma closest to the identity not in G1. Then take G3 to be the subgroup generated by G2 and the element in gamma closest to the identity but not in G2. We continue this construction until we exhaust gamma, and this sequence of subgroups exhibits gamma as a nilpotent group. Using Turing's result, Sachik-Gelander proved that if X, a limit of almost homogeneous spaces, is compact, then it is a torus, that is, a finite or infinite product of circles. As a corollary, one gets that the only compact topological manifolds that one can obtain as limits of almost homogeneous spaces are tori. Part 5. Lower semicontinuity of the fundamental group under convergence with discrete symmetry. What we were able to show is that if we have a sequence of almost homogeneous length spaces and the limit is semi-locally simply connected, our standard assumption, then the limit is a nilpotent Lie group equipped with an invariant Finsler or sub-Finsler metric. And for large enough n, there are subgroups lambda n of the fundamental groups of xn and surjective homomorphisms from lambda n to the fundamental group of the limit. One can see that these groups lambda n are in a sandwich between the fundamental group of xn and the fundamental group of the limit. They are, in some sense, smaller than pi1 of xn because they are subgroups, and at the same time larger than pi1 of x because they surject there. So in some sense, the lower semicontinuity of the fundamental group still holds for sequences of almost homogeneous spaces even in the non-compact case. I also want to point out that by the Anne-Montgomery and Leo-Tzipin solution to Hilbert's fifth problem, we can replace the semi-local simple connectedness hypothesis by the assumption that X has finite topological dimension. From now on, I will talk mostly about the proof of this theorem. The proof splits into two parts. First, proving that X, the limit space, is an nilpotent Lie group, and then proving the lower semi-continuity of the fundamental group. To show that X is a topological manifold, as a first step, we construct gamma alpha, the equivariant ultralimit of the sequence of groups gamma n, with respect to some non-principal ultrafilter, and check that it acts transitively by isometries on X, making it a locally compact homogeneous length space. In the 80s and 90s, Valery Berezovsky developed some general theory of locally compact homogeneous length spaces. In particular, he showed that X is the projective limit of the sequence of the form Gm over Km, where Gm is a Lie group, Km is a compact subgroup, and the quotient is equipped with a Finsler or sub-Finsler metric. The convergence of these quotients to the space X is way stronger than pointed Gromov-Hausdorff convergence, since Dm globally looks similar to X for large M. To prove this result, Berezovsky uses extensively the Gleason-Yamabe solution of Hilbert's fifth problem. Then we apply more heavy machinery, that is, the quantitative version of Gromov's theorem on groups of polynomial growth by Amanieu-Breuilat, Ben Green, and Terence Tao. That theorem implies, due to the local compactness of X and the discreteness of the groups gamma n, that such groups are almost uniformly virtually nilpotent, in the sense that they have subgroups of bounded index with the property that all commutators of certain fixed step are small. Taking the limit as n goes to infinity, we get that the groups Gm are all nilpotent. The next step will be observing that compact subgroups of nilpotent Lie groups are central, and for faithful actions, a stabilizer can only be normal if it is trivial, so the actions of Gm on Zdm are free, and we can identify these two spaces. Finally, using the semi-local simple connectedness hypothesis, we are able to show that the sequence Gm stabilizes, and X is a nilpotent Lie group. Then what we do is quite tricky. We go again over the same argument, but with the a priori knowledge that X is a nilpotent Lie group. This allows us to use results from sub-Finsler geometry like the local uniform doubling bound of Nagel, Stein, and Wenger, and the recent result by Enrico Ledon and Alessandro Tazzi stating that the isometries of X are smooth and uniquely determined by their first-order behavior at any point. With these tools and some juggling with the Baker-Campbell-Hausdorff formula, we obtain that the group gamma alpha acts on X by translations, and the groups gamma n of the original sequence act on the spaces Xn almost by translations. Now we go back to the definition of pointed Gromov-Hausdorff convergence. We have maps Fn from left to right and Hn from right to left, which are almost isometries on balls of increasing size, and the compositions Fn-Hn and Hn-Fn are close to the identity on such balls. These Gromov-Hausdorff approximations will help us build maps phi n from gamma n to the group of isometries of X. For G in gamma n, if G doesn't drift Pn too far away, then the composition apply first Hn, then G, then Fn, is close to being an isometry on a large ball around P. Then we define phi n of G to be the isometry of X closest in such ball to that composition. By the previous analysis and the fact that the groups gamma n act almost by translations, we get that phi n of G is close to a translation and close to the composition Fn, G, Hn, so the diagram almost commutes in a large ball around P. If you know Gromov's proof of his theorem on almost flat manifolds, you may notice that I built this map with the same intention he built his holonomy map, and we will use it in a very similar way. As n grows larger and larger, this square is closer and closer to commute, so for large enough n, the map phi n behaves so well that one can find small normal subgroups Hn, which very informally we should think as the kernels of the maps phi n, such that the quotients gamma n over Hn near the identity behave like large discrete subgroups of Lie groups. and large discrete subgroups of Lie groups have a very particular structure, Broglie, Green, and Tau, called nil progressions. They are found with the short basis trick we used earlier to prove Jordan's theorem. This is the same trick Gromov used to find the nilpotent structure in his proof of the almost flat manifold theorem. For a positive C, a C-regular nil progression is a very simple object with a slightly complicated definition. A C-regular nil progression is a subset of a group built out of D-generators, U1, U2, and so on until UD, and the dimensions N1, N2, and so on until ND. A piece of the nil progression consists of elements of the group which can be written in a unique way as a power of U1 times a power of U2, and so on times a power of UD, in such a way that the power of Ui is smaller than Ni over C. We also require the further property that the commutator of Ui and Uj lies in the span of Uj plus 1, Uj plus 2, and so on until Ud, with some technical control on the exponents. We usually think about nil progressions with the additional assumption that N1 is much smaller than N2, which is much smaller than N3, and so on. So, I told you they had a complicated definition, but they were actually very simple objects, right? Let me give you a couple of examples. One can take this blue box of elements in Z2 and observe that if we take U1 to be 1, 0 and U2 to be 0, 1, then every element in the blue box can be written in a unique way as a power of U1 times a power of U2. Also, U1 and U2 commute. The next example lives in the Heisenberg integers, the 3x3 upper triangular matrices with integer entries and ones on the diagonal. If we take U1, U2, U3 to be the standard set of generators, we can observe that if we bound the entries of the matrix, getting a blue box like the one in the picture, any element in such blue box can be written in a unique way as a power of U1 times a power of U2 times a power of U3. Furthermore, the commutator of U1 and U2 lies in the span of U3, and U3 commutes with everyone else. And in general, all C-regular nil progressions look very similar to these boxes. By a classical theorem of Malcev, these boxes can always be taken as subsets of simply connected nilpotent Lie groups, provided the dimensions Ni are large enough depending on D and C. Fortunately for us, that is our situation, and the groups gamma n over Hn are isomorphic to quotients of lattices in simply connected nilpotent Lie groups. Now, we use the crucial property of nilpotent Lie groups that they are simply connected if and only if they are torsion-free. Again, nilpotent Lie groups are simply connected if and only if they are torsion-free. To finish the proof of theorem Gromv, we observe that for every non-trivial loop of X corresponds a torsion element of gamma alpha. Through the almost homomorphisms phi n, we can pull back that torsion element to an almost torsion element of gamma n over Hn, which translates into a non-trivial loop in Xn. So we are exploiting the fact that on nilpotent Lie groups, we can take the topological property of having a non-trivial loop and translate it into the algebraic property of having torsion, and then translating back that algebraic property into the topological property of having a non-contractible loop. And this finishes the proof of theorem Gromv. Of course, as a corollary, we obtain that the nilpotent Lie group obtained by Kapovich, Bilking, Broglie, Green, and Tau is simply connected. Now I want to finish this talk with a couple of questions that arise naturally out of the proof of theorem Gromv. First question is, which nilpotent Lie groups can arise as limits of almost homogeneous spaces? If one analyzes carefully the proof of theorem Gromv, one can translate this question into a question in nilpotent Lie algebras. Is it true that the structure coefficients of a nilpotent Lie algebra can be approximated by structure coefficients of nilpotent Lie algebras that admit lattices? My second question is, can we replace lambda n in theorem Gromv by the fundamental group of Xn just like in the compact case? Again, analyzing the proof of theorem Gromv, one can translate this question into a question of nilpotent Lie algebras. Is it true that for any nilpotent Lie algebra, the dimension of the abelianization is at least the dimension of the center? I'm not an expert in nilpotent Lie algebras, but my personal guess is that these questions are not that hard to solve. Now a much harder question will be the following. If we have a sequence of proper length spaces xn converging to a nilpotent Lie group X equipped with an invariant metric, and we have groups gamma n acting discretely and one transitively on the sequence xn, can we find subgroups of pi1 of xn that surject onto pi1 of x? In other words, is discrete symmetry enough to force lower semicontinuity of the fundamental group? And that's it. Thanks for watching.